specialized thing. Some of those people also do cosmology and some don't. Is that your question? Yeah. Okay, so I guess I already said this. But the cosmology theory, the theory of the universe, I mean, the fact that the universe is comprehensible is amazing, and the theory of it really just depends on knowing what are the fundamental particles, what are the forces, and the very early universe is, an amazingly simple place, very smooth and weakly coupled. And so really, if you just know what the equations are, you can just apply them to the very early universe in a straightforward way, and vice versa. By making observations that depend on what happened in the universe, you really can learn about very fundamental things without a lot of messy intermediate computational layers. And okay, so here's one picture of the universe. People sometimes show a pie, or sometimes a cupcake, or sometimes a jar of jelly beans to represent the universe. And what does this represent? So this is sort of a way of making friendly our picture of what the constituents of the universe are. So the constituents of this jar are, some things are colored jelly beans, and some are black. And you notice it's mostly black. And that is literally what we know about the universe too, that we know that most of it is some kind of stuff. We call it dark matter, dark energy, and we don't know much else about it. I'll get in subsequent lectures what we know and don't know about those things. And then there are little bits represented by the light jelly beans that we can describe with our standard model of particle physics. Although even within our standard model of particle physics, we still have some theory to do to explain how those standard model particles got there, why they are there in the abundance that they are. But we are developing a quantitative consistent theory. We know most of the matter is dark. We also know, this is the phenomenon I alluded to called dark energy, that empty space, vacuum, sitting there by itself, for some reason, has a tendency to expand. And will always do that. You can't get rid of it. Or you can fit that into your equations by saying that empty space has an energy density without any matter being there. We call that dark energy. And the very early universe at some point, we know this, went through a period of expansion that was very violent, much more rapid than what we're going in now. This is called inflation. I'll get to that in the fourth lecture, at least that's the plan. That diluted pretty much all the ordinary matter and left the universe in a very smooth state without any matter. And then we have to go back and explain how we got here. This is how the ordinary matter got made. This is what's called baryogenesis, which I'm going to talk about in the third lecture. So, okay, so what am I going to do today? I'm attempting to be very basic today to talk about, what does it mean for space to expand? What are the basic concepts of general relativity, Einstein's theory of gravity? What is a metric? Things like that. What is our basic picture of cosmology? Why we think there's a Big Bang? And then tomorrow I'll talk about the dark matter, which is more a particle physics topic, and then talk about baryogenesis, which is a very early universe topic, how we got here, and finally, dark energy inflation for the last lecture. At the very end, to about out in the sky, and that's what we're doing. So this is Newton's basic law of motion. First of all, that an object that is not being acted on a force will go in a straight line. We'll modify all of this. I guess I would say it was wrong, or at least kind of an approximation to a much more deeper and profound facts about gravity and space and time itself. So I understand you've taken special relativity, right? So you know about space and time being unified, being describable in the same framework, and even different observers having different opinions about what's space and what's time. But general relativity explains that space and time is really completely exactly the same thing as what gravity is. They go together, they can't be separated, and this explains a lot of things. Of course, having discovered this, he wanted to, which so far we haven't done. But let me give you this thought of Einstein's, which is how he started on this path of understanding space, time, and gravity. He was sitting on a chair, apparently, and I don't know if he fell out of the chair, but he had the thought, he said the happiest of his life, that when falling, you don't feel your own weight. And that is the same experience you would have if you were floating around in space. So somehow, in free fall, the experience is exactly the same as floating around in space. So what is gravity if it's something that you can sort of turn off by being in free fall? So this reason, the fact that free fall is the same as gravity, is something that we know even in Newtonian mechanics. It's called the Equivalence Principle, which is that all gravity cares about is what is the total mass of an object, and the inertial mass. The gravitational mass is exactly the same as the inertial mass, exactly. And when two things are exactly the same, it's probably not a coincidence, but it is a coincidence in Newtonian theory. So Einstein set out to figure out why is that? I mean, it can't just be a coincidence. It shouldn't be. And realized that you have to come up with a theory about space and time in order to do that. So there's two ideas, and I'm not going to do the full general relativity equations ever in these lectures, but one is that space and time itself, if you think about, you could represent space and time as this kind of grid. This is just showing 2 dimensions out of the 3 space and 1 time dimension. And you can see this grid, which we always use to sort of draw pictures of space and time, is 2-dimensional. And in order to show the curvature, we show it as embedded in 3 dimensions. But in order to really think about general relativity, you have to be able to accept, of course you can't really picture, the idea that you can just have intrinsically a curved grid like that without it having to be embedded in a higher dimension. So this represents space and time as a grid, and the Earth here as warping the grid, causing it to be distorted. And so that's part 1, that space and time can be warped by matter. And then part 2 is that all gravity is exactly the same thing as what acceleration is. So the thought experiment here is, imagine this person in an elevator and they're weighing a fish on a scale. And here's the free body diagram for the fish. Here's the weight force, and there's the tension force, and then the scale measures the tension force, and that tells you what the weight of the fish is. So if this box is sitting on the surface of the Earth, the fish will weigh whatever it weighs. Or if you were to take this box out into empty space, far away from the Earth and its gravity, but pull it with a rope with an acceleration of 9.8 meters per second squared, same acceleration, so you keep pulling this faster and faster, then the floor pushes against the man's feet, the roof is accelerating away from the scale, that pulls on the scale pulls the fish along, and the scale also measures the same weight. So you can't tell whether this fish has weight because it's in the gravitational field of the Earth or because it's being accelerated. Similarly, if you are in free fall, it's just like turning off gravity. So here's a picture. It's called the zero-G plane, but it's colloquially called the vomit comet, because I guess that's what the experience is like. But that would, that could happen. Okay, so the basic key ideas without equations then, I haven't done any equations. If it's observed, at least locally, you're not going to observe the effects of gravity. So according to this picture, we're not inerrant. We introduced this whole notion of curved space and a metric in different frames, inertial or not, can agree on. Yeah. Okay, and general relativity was famously confirmed when the bending of starlight was observed during an eclipse, so that stars that were behind the solar eclipse were still visible because the light was bent. Gravitational, we call that gravitational lensing. This became worldwide headline news. And, okay, general relativity just keeps going on with amazing facts. One thing Einstein was troubled by about his equations is that a static universe was not consistent with them unless he added a term called the cosmological constant. Now, so that seemed to be a blunder because, I don't know why Einstein wanted a static universe, but people have always wanted a static universe until they discovered that it's not true. But Hubble discovered that when you look at galaxies, distant galaxies, and observe the spectra, the atomic spectra of the light being emitted, that the spectra are shifted towards the red, longer wavelength. And this could be interpreted as a Doppler shift from the galaxies moving away from us. And the more distant galaxies were moving away faster. In general relativity, what we interpret this as is just that space itself, represented by this grid, is just expanding. So these grid points we call co-moving coordinates. You can imagine different galaxies just sitting there at rest in the co-moving coordinates. But the space itself is expanding. And what about the light? Well, if light comes from one galaxy, while the light wave is traveling, the space expands and the wavelength also gets stretched out. So that's a different interpretation of the Doppler shift, that it's actually due to space itself expanding, the wavelength itself expanding. We call that the redshift. And even though this isn't really cosmology, at least not yet, I can't resist. Everybody heard about gravitational waves being detected last year. Another famous prediction of general relativity is not only does matter warp space-time, but if you get very violent events, they will cause it to shake, and the waves will propagate. And the shaking caused by two black holes annihilating 1.2 billion years ago were observed and announced by LIGO last year. They have since observed 3 more such. Let's see how fast I'm going. Okay, this is pretty good. Okay, so let me just recap. I've done everything without equations so far. And this would be a good time for questions too. So I've talked about how gravity is the same thing as dynamical spacetime, according to Einstein's theory of general relativity. And if you're not familiar with that concept, you probably haven't absorbed it yet. But anyway, it's out there. Talk about it. And that energy, not just matter, distorts space and time according to Einstein's equations. And then stuff follows geodesics in space-time. And there is a limit in which this reproduces Newtonian gravity, where things are moving slowly, et cetera, and the gravitational field is weak. The equivalence principle is automatic, and the gravity is indistinguishable from being in an accelerated frame. Okay, so slightly more technical? Yes, yeah, question. Yes, space is expanding, yes.
Only in one direction?
No, it's expanding in all 3 directions. Yeah. Oh, like you can only represent so many dimensions on a picture. Yes. So. Yes, and it's also impossible to imagine, but because when you think of it expanding, like when I draw a picture, you're going to show some points as being fixed and other points as moving away from them. And the actual math of that can be done in such a way so that there's no special point in that expansion. Everything, no matter where you are in the universe, everything is receding away from you uniformly in all directions. Yeah, so here we look out and galaxies everywhere are receding away uniformly. That means no matter which direction we look, we'll see a galaxy point. It must be blue shifted. Yeah. So there's the Hubble law is true on the average, but there are a lot of little deviations from it because the galaxies, besides just being, you can think of them as bedded. Yeah. Means that use this metric tensor, G mu nu. G mu nu is just got a -1. It's just diagonal to figure out what's going on. But then we try and compute generally coordinate invariant things. Okay, so now we want to apply this theory to the universe as a whole, to space-time as a whole. And this is cosmology. So if we just start with the assumption that the universe is completely smooth, which obviously isn't true, but it is true on the largest scales as far as we know. And it was pretty close to being true very early on as far as we know. And was completely spatially homogeneous, the same everywhere at a certain time slice, and completely isotropic, the same in all directions. This is the cosmological principle. And we then write a metric tensor consistent with that in some coordinate system. We can choose our coordinates so that the metric tensor has this form. There's no mixing between the time and space. The interval squared goes like minus dt squared. And we choose coordinates, so there's just a -1 here. And then here's the important thing. The scale factor is called A of t. It can only depend on t by the cosmological principle. It can't depend on where you are. This describes what the physical distance is between 2 points that have the same co-moving coordinates. And then we're allowed to assume that space as a whole, consistent with those conditions, has constant curvature everywhere. The curvature can be positive, or it can be negative, or it can be 0. Any of those are consistent with the cosmological principle. Positive curvature can be described by a metric where we put a 1 here in this equation. Negative curvature by putting a -1 here for this k. And flat space can be described by putting a 0 here. And then this is most simply written in spherical coordinates. Although if curvature is 0, then it's also pretty easy to write in Cartesian XYZ coordinates. Okay, so this is the most general thing. So we take this for our metric tensor, and we apply Einstein's equations of general relativity to it, given what we know, and we get an equation for what the rate at which the universe is expanding. And conventionally, we take T naught to be now, and we take our scale factor to be 1 now, and because we know the universe is expanding, a scale factor was smaller in the past, this A of t was less than 1 in the past and greater than 1 in the future. In fact, if we just extrapolate the expansion rate we see, if we assume it was expanding at the same rate, we find that this scale factor goes to 0 at some finite point in the distant past. Then the Hubble parameter is the rate of change of A over A. Notice this has dimensions of 1 over time. And it's on the same order of magnitude by dimensional analysis as the age of the universe, the inverse Hubble parameter. Okay, and the thing that is always fun and interesting and sometimes confusing in doing general relativity is we use these coordinates, they call them co-moving coordinates, but physical distances depend on the metric, and for this metric, they depend on the scale factor. So like we could take 2 points, 2 galaxies far enough away so they're not going to be pulled, 2 test particles. Their co-moving distance stays the same, their physical distance is increasing with the scale factor. And the redshift is really a lot about how we've determined much about the expansion of the universe in the Big Bang. This is due to the fact that the wavelength of light expands along with space. Atoms emit light at certain very specific wavelengths, so you take the spectrum, you know what kind of atom you have, but then you observe the light emitted from distant galaxies, and you find the spectra have been shifted towards longer wavelengths. And so the difference between the observed wavelength and, assuming they have the same laws of physics over there, the emitted wavelength gives us the redshift. 1 plus the redshift is that ratio. So redshift of 0 means there's no redshift, and the emitted wavelength is the observed wavelength. And we can use redshift as a proxy for how far away things are and how long ago the light got emitted. Redshift 0 means they're pretty close, and large redshift means the light came from when the universe was much smaller and younger. So the distant galaxies are receding with a velocity. The Hubble law is approximately linear, the Hubble constant over their distance from us. So for galaxies that are pretty far away, like 10 megaparsecs away, the velocity is 10 to the 3 kilometers a second. Once you get into much bigger distances, you find the velocity can be the speed of light or even larger. And what does that mean? Well, the galaxies can recede from a special relativity together. Then the most distant represented as a very uniform. It can only see the surface of. So we can describe space-time dynamics using a metric tensor. And then if we get a specific form for that metric tensor when we take the cosmological principle, and when we combine that with observation and general relativity, we get this expanding universe with this metric tensor. The most important part of this metric tensor is just a scale factor that changes with time. We know this because of the distant galaxies apparently receding due to the redshifted light, which we interpret as the scale factor increasing in time. And the most distant object we can observe is the cosmic microwave background surface of last scattering, which is a very big object, fills up the entire sky. Any questions about that? Yes?
Does the galaxy, the space-time, expands at constant acceleration?
That's a super interesting question. Does it expand at constant acceleration? Yeah, this is really, so a lot of cosmology now turns to that question. How does the rate of expansion change with time? And a lot of observation has gone into that. That's a very long story. The answer, as far as fairly recently, when the redshift was about 1, a little later, the expansion rate started to accelerate again due to dark energy. That's our story, okay? And so why all the, I'm going to get to that, I think, at the soon. That's sort of what the rest of this is about. Any other questions? Yeah. Yeah, so there's some issues. You have this story. So this extrapolation back into the past, using everything we know, implies that we can extrapolate back to the CMB when the scale factor was 1,000 times smaller, and we infer the universe was younger. But if you keep going back, you find the scale factor was 0 at some finite time in the past, which means there wasn't any space. Presumably wasn't anything. And you can't imagine that. So we call that the initial singularity when the universe was infinitely dense. then the fact that the cosmic microwave background, as observed, is a black body spectrum implies something thermalized it. And furthermore, it's the same temperature everywhere, which implies it was all in thermal contact. And that's a puzzle because there wasn't enough time, given that the universe was only 375,000 years old when that happened. There wasn't enough time for it to have been in thermal contact. So why that? And then, of course, we would like to understand the equations and the behavior of the scale factor of the universe from the beginning of time to now and why it was doing that. We have dynamical equations now. Now we have to get into Einstein's equations. And it turns out that, okay, you could just plug in the metric tensor that I wrote down into the Einstein's equation and determine these equations, but it's actually possible to get what comes out pretty easily by waving your hands. Let me do that, okay? So there's really two important equations that come out of that. And the hand waving, it really has enough physics in it. I mean, it's kind of right. So there's energy conservation in a sense. So, if you've got a volume of stuff, like stuff inside some container, and you expand the container, if there is pressure, the amount of energy inside will change according to... You're sitting here and you're looking at some test particle over there. It's a unit distance away. Its velocity is going to be 1/2 times the change in the scale factor with respect to time squared. And so 1/2 v squared is proportional to the kinetic energy. And what about the potential energy of that particle, which is sitting a physical distance a away? So if we imagine some uniform energy density, gravity inside this material, epsilon, so the total amount of energy is a cubed E, and the gravitational potential energy, there's some perfect balance. But if we had spatial curvature, we'd have a different constant here. All right, so it usually gets written in a different form. And can I turn on a light so I can write on the board? Because I have time to derive it. Side. Squared equals, so epsilon critical, the critical energy density, is 3h squared over 8 pi g. Okay. Yeah, I have that there. And this is often called omega critical. Okay, so we observe the Hubble constant. We know what the Hubble constant is. This defines a critical energy density. And we now start trying to figure out what the composition is of the universe determined in units of the critical energy density. This critical energy density is a very important concept in cosmology. And, okay, so this isn't enough to figure out what the scale factor is doing. We need a relationship between the pressure and the energy density. We've got three quantities now. We've got the scale factor, we've got the energy density, we've got the pressure. They're all changing in time. We have two equations from general relativity. We need a third equation to be able to figure it out. So that third equation is called the equation of state, which relates, if we have some stuff, relates its energy density to its pressure. So we sort of chop, the composition of the universe up into different kinds of stuff, and each kind of stuff has its own equation of state. So for, we'll call it dust or particles, most of the energy is just their mass, E equals mc squared. And there's basically no pressure if they're just sitting there at rest. So we call that matter or dust or cold particles. The equation of state parameter is 0. We can throw out the pressure. For radiation, which would be any kind of massless particles, that would include light. And as far as we know, the other thing it could include is neutrinos, which have a little bit of mass, but you can ignore it. And so for radiation, that equation of state parameter is a third other way around. P equals, okay. And for vacuum, it's -1. I think I wrote this equation. It should be P equals WE. But, yeah, I should write that down. Okay, so what about this vacuum which has pressure equals -epsilon? So this comes about from, what is the vacuum? We assume it's some state which is Lorentz invariant. So if we write down the stress tensor, it looks like T mu nu. It's got energy, P, 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 and zeros everywhere else. Energy and pressure, that would be like, and if you set the pressure equals to minus the energy density, then that's completely Lorentz invariant and is a fine vacuum state. So another possible component of the universe, which we didn't expect, but which seems to be there, would be just that the vacuum itself has energy, and that would correspond to negative pressure if it had positive energy density. And then, okay, so now we've got 3 equations, solve them. I'm not going to do that. That could be an exercise, just solving differential equations. If there's no pressure, the energy density just goes like 1 over volume. This kind of makes sense. You just have energy, you dilute it as you expand space. It goes like 1 over volume. And then you plug that back into the other, and you find that the scale factor grows like time to the 2/3. If you have radiation, then it dilutes faster because not only does the number of photons dilute, but their energy goes down as their wavelength gets longer. So the energy goes like 1 over 8 to the 4th. So this universe, a radiation-dominated universe, doesn't grow quite as fast, only like chi to the 1/2. But if you have vacuum energy, the vacuum energy, the energy density of the vacuum is just constant. This is kind of a crazy thing. You can have vacuum, it sits there, it just expands, the energy density is constant. It seems like you're just creating energy because you're creating more space, and the space is filled with energy. But the negative pressure takes care of the concept of local energy conservation. So somehow, this is considered okay. And you find your scale factor then, A dot, if this is constant, A dot is constant. If A dot is constant, the solution to that equation is an exponential. So the scale factor then grows exponentially fast. And notice there's a huge difference. If you've got vacuum energy, not only does the scale factor grow exponentially fast, but you can extrapolate arbitrarily far into the past. So a universe that was just filled with matter or radiation, we would have a finite time in the past when the scale factor went to 0. Energy. Call it dark energy. Anyway, some stuff with negative pressure. This is inferred because the scale factor of the universe actually is growing at an accelerating rate. 23% is some kind of stuff we call dark matter, which I'll talk about tomorrow. 4% is ordinary baryons, atoms, mostly hydrogen and helium. Mostly non-luminous, just gas floating around. A little tiny bit is the stars, and an even tinier bit that doesn't even show up in this pie chart is the neutrinos and the radiation. But if we look at it, if we back in time, so here's the universe here and now. We see that, and this is a singularity in the center, and there may have been an initial singularity. Yeah, a black hole does not tend to expand necessarily. Yeah. So it's kind of philosophical. In a different space. There's a lot of speculation about that. It's not necessary. I mean, it's not necessary that you imagine that the space is embedded in higher dimensions or that, but you can speculate about it. And you can people have written down theories that they like in which that is true. And the equations are not necessarily ruled out. Yeah? I mean, it's kind of like you could, I mean, when we draw pictures of curved space, we always draw two-dimensional surfaces that are, in order to draw them, we draw them embedded in higher dimensions. But you could imagine something that was just completely intrinsically two-dimensional, and there wasn't any need for the higher dimension as well.
Because of the expansion in the Big Bang itself, is there any evidence that happens not far in history that also causes expansion?
I mean, besides the Big Bang? I mean, there is evidence for the Big Bang, right? The fact that we observe the cosmic microwave background, the fact that the distant galaxies are receding. Those are big pieces of evidence for the Big Bang. Earlier than that, we can't see. It's opaque. Any part of the universe start to expand? No. I mean, if some part of the universe pinched off and formed its own universe, I don't know that we would really notice anything. Yeah. It would just form its own space. It wouldn't blow up in our space, right? Yes?
The major bodies that we depend on to see, the matter of the expansion of the universe in the large distance is supernova. That's right.
So
the question is,
it's not the only way, but it is the most important way right now. Yeah.
I read in the historical side that the reason days that they have developed more precision chemical way to see those bodies, and
Right. You need to be able to determine the physical distance in some way other than the redshift, and there's a type of supernova which are standardizable.
What I want to say that they say that we see the universe expanding on some scale or for some distance. Does not necessarily that the whole universe is expanding. Just like that we for Andromeda or the local group galaxies, they does not expand.
Right, the local group is not expand.
But in the more distant, the universe is expanding. So is that possible that for more massive scales that we have not even until now seen that?
So most of our evidence is going out to redshift of a few, and yeah, so beyond that, we don't really have redshift.
Maybe that maybe randomly, not necessarily expanding. Is that possible?
Are you saying is it possible that the observations we've made about the supernova are wrong?
Yeah.
So people have, so you infer the supernova distance from it being a certain type of supernova whose intrinsic luminosity you can determine, and then from how luminous you actually see it to be. And there could be systematic errors there. People study that a lot.
Yeah.
That's an important question. Yeah. Yeah, there are other types of, something that is maybe less subject to certainty, but it's complicated to explain, is in the cosmic microwave background, you observe a certain preferred scale in terms of, about a degree on the sky for where the temperature fluctuations are the largest. So somehow the fluctuations, and we have a theory for where that 1 degree comes from, but then you propagate that forward in time and you should observe a peak in the galaxy correlation spectrum at about the same place, about where, the same, and that gives you sort of a standard distance, which is a function of redshift. You can also use it's called baryon acoustic oscillations or something like that. But yeah, there are other methods that you, the what? You mean besides space and time? Or what is in space and time, or what is space? So that sounds more like a philosophical question. Yes.
We know that there are gravitational energy between the particles of the universe.
Yes.
If we can explain, so what makes this is what is the force that
Due to the fact, the gravitational force, you could think. And so what causes that? We can describe it with equations that include dark energy and negative pressure, which negative pressure anti-gravitates, if you like, according to those equations. Will they send them to you and you will ask them? Okay.
So it's